Question 4 says, the circuits of figure 4 are the same as figure 3, except that a source or component has been changed from a fixed value to a variable one. Find I, the value of R in figure 4a, at which the diode is on the point of changing from a conducting to a non-conducting state. 2, or II, the value of I in figure 4b, at which D2 changes from a conducting to a non-conducting state. Has the state of D1 changed under these new conditions? And III, the value of I in figure 4c, at which D2 changes from a conducting to a non-conducting state. Has the state of D1 changed under these new conditions? So, let's have a look at question 4a. And again, I'm going to go through the same method as is gone through in the answers, and the reason for that is the same as before. Not because there will be conflicting answers, there won't. There is exactly one right answer. It's just I don't want to give out multiple ways of solving the problem, because that could be quite confusing. So question 4a then, I'll just draw out the question. We have, I'll try and draw it over here so I can work in the middle. Current source, resistor, another resistor, another resistor, and a diode. And this one is now R. This is still 3K, that's still 2K, and this is 4K. And there's 10 milliamps down here. Because the diode is on the point of conduction, we can draw an arrow there that says 0.7, and we can go for our other usual thing, which is that the current here has to be 0 amps. This is a standard, same as in question 2. And then we can put some loops on. And the loops we'll be choosing are that I1 goes down here like this, around there, and up there. And that we'll call it I1. And we have I2 on the top. And we have I3 in the lower part. Alright, so then we can write out the voltages around the loop for I2. So we're gonna write out what's going on here, and we will say we're going to start with R. So our voltage here will be that way because the current's going up the page, and the voltage here will be that way, and the voltage here will be that way. And we know this one's 0.7, so you can treat this as if it's a battery. So we'll do I2 times R plus, and I2 is the only current in R, plus I2 times 3K minus, because we've got 10 milliamps is I1 going up the page, so that acts to lower the voltage across the 3K due to I2. So we'll put I1 in, we'll substitute later, minus I1 times 3K, and then we've got the diode, which we know at the moment is a 0.7 volt source, and that's added. It's added because the 0.7 volt and the voltage that we've got due to I2 are facing the same way. If it's facing the other way, this arrow was like that, or if I'd chosen my loop to be the other current flowing the other way, I'd have ended up with a minus there. So we can squooge that lot together to give us. I may deviate slightly from the given result or method, but essentially it's the same thing, just the algebra is slightly different. It's actually incredibly difficult to work through other algebra while talking. So it's R times plus 3k minus I1 times 3k plus, it's all equal to 0 by the way, 0.7 equals 0. And we know that I1, so other thing you can say is I1 equals 10 milliamps. Because that branch current is downwards and I1 is also downwards, and there is the only loop current that can represent this branch current is I1. So there are no other currents involved in this 10 milliamps. I1 must equal the 10 milliamps. So we can say that I2 times R plus 3k equals minus 0.7 plus 10 times 3k. And that's the 10 milliamps from down there. So this we'll call number 1. And then we'll have to do something else because we can't solve this at the moment. We have to have another loop. So we'll do the I3 loop. We'll do this loop here, I think. Yeah. I'm just making sure I'm choosing the same loops, because if I don't, we'll get the same answer with different maths and that might be confusing. So we'll do the I3 loop next, and we'll say I3 times 4k. So that's that voltage there. And we've got another voltage here due to that, due to I3 in the 2k, and the I1 that flows through the 2k acts to make this voltage smaller. The other important thing to know is that this arrow and this arrow face the same way, and this arrow is opposing. So when we come to put this into our equations, we'll need a minus sign to take account of the wrong direction of the arrow, because all the loop voltages have to add up. So that plus that plus that must equal 0, except that this is facing the wrong way, so that plus that minus that must equal 0. Righty, so yes, the I3 is the only current in the 4K, so we can carry on now and go over to the 2K, and we'll say plus I3 times 2K minus I1 times 2K minus 0.7 is equal to 0. So then we'll solve this for I3, because we already know what the value of I1 is, it's 10 milliamps. So we'll get I3 on its own, substitute in I1 and solve it. So we'll do I3, open brackets, 4k plus 2k, so that's that term there and that term there, minus 10 milliamps times 2k, so that's that term there, and I've substituted in I1 as well. Minus 0.7 is equal to 0. So we'll take that lot over and divide by this bit here. So we'll get I3 is equal to 10 that's a times. 10 times 2k minus plus 0.7, plus because I took it over the other side. If you don't like the idea of taking this over there, you can say I'm going to add 0.7 to both sides, and that means that this will disappear because you'll have 0.7 plus 0.7, which is nothing, and over here you have plus 0.7, which is the same as you got there. Divided by 4k plus 2k. We don't really need the brackets anymore, but whatever. And we can do that and get a result. And it will be 10 times 2 plus 0.7 is 20.7 divided by 6k, 3.45 and this is milliamps. Right, so then we need to go about getting ID. So ID must be 0, and ID is a combination of I3 and I2. Because we've got a branch current here, which is the branch current in the diode, and that must be 0 because the diode's on the edge of conduction. And this branch current is a combination of I2 and I3. In fact, ID is equal to I2 minus I3, and I know that because I'm looking at the direction of the arrows. So what we'll do then is we'll say ID is equal to 0, first of all, we know that's true, and we'll say that ID is also equal to I2 minus I3. Now we know what I3 is because we just worked it out, this was I3. So we can say that I2 is equal to minus I3 minus ID. Or rather, I2 is equal to minus I3 because this bit's 0. So we've got I2 is equal to minus 3.45 milliamps. And the reason is this bit here is 0. Oops. And the reason it's 0 is because the diode is on the edge of conduction. So we've got to do something to R to make I2 minus 3.45 milliamps. So from our original set of equations, which I've now rubbed off for the I2 loop, I had something along the lines of I2 brackets 3k plus R equals 30 minus 0.7. Now it may be that I had this 30 composed of other things, because I think I wrote out something a bit longer than that, but it is the same, and you can work through it to find out what I had originally. And that's 29.3 volts. So we can say that I2 is, or I2 equals 29.3, sorry, 29.3 divided by 3k plus R, and that I2 must be equal to I3 from up here, so we can say that equals to 3.45 milliamps. So we can then multiply through and say 29.3 is 3.45 times 3 plus 3.45 times R. Take that, sorry, that's times. Take that across, so I'll have 29.3 minus 3.45 times 3k divided by 3.45 is equal to the value of R, which is 29.3 minus 3 times, sorry, 3.45 brackets 3.45 times 3 divided by 3.45, 5.4927 kiloohms. So 5.49, next thing's a 2, but it's 7 after, so it rounds to 3 kiloohms. And that value of R will yield 0.7 volts across the diode and 0 amps through it. Moving on to question 4 part B, We are back to the circuit with two diodes. Righty. So the question is asking us to find the value. The question is asking us to find the value of I. Oh, sorry. It's not 10 milliamps. It's an unknown current. An unknown current I, which D2 changes from conducting to non-conducting, and it asks, has the state of D1 changed under these new conditions? So what we're going to have to say is, well, this is D1 and this is D2. So we've got D2 is on the edge of conduction, so 0.7 volts across it and no current through it. And we know from before that D1 was not conducting. So we can do away with D1 because we can assume that it's not conducting again. So D1 disappears. And we can use loop analysis, and we'll develop 3 loops, and these loops will be I2, ID, just make that resistor look a bit better. Not a very good one. So that'll be ID. And there'll be I1 as well. And I1 is now the unknown current, because I1 completely describes the current in the unknown source. And we can also say, as we did before, that I2 must be minus 20 milliamps, because I2 completely describes the current in this source and the arrow direction is different. So I2 minus 20 milliamps. And we know something else. We know that ID must be 0. Because ID is the only current flowing in the diode, and we've decided that the diode is on the point of conduction. And that means no current flowing through it and 0.7 volts across it. We can, strictly speaking, I suppose we can also write that I1 is equal to the unknown current I, which is what we're looking for. So we can then write out a loop equation for ID, and we'll say that Oh, I haven't written any resistor values, have I? Better put some resistor values on, otherwise it's going to make the problem a bit too difficult to solve. We had 2K and 2K and 10K and 1K. Starting with the ID and the I1 and the 10K, we'll have ID times 10K, which gives us this voltage here, minus I1 times 10K, which is that voltage there, which is these two subtracting from each other. So this one I'm calling positive because I'm worried about ID, or the current in this loop. So minus I1 times 10K, and then plus 0.7, because we've got the voltage source here. You can put a battery in there if you want to. And then it comes down here, and we've got ID times the 2K. And then we've got ID times this 2K as well. But first, we've got I2 here as well. So we've got minus I2 times 2K. And we've got the voltage there due to that 2K, which is plus ID times 2K minus I2 times 2K is equal to 0. So we can squash this down by factoring it into what the resistors are, because we've got 10K and 2K and lots of currents. So matter of fact, all of these are voltages, because we've got amps times ohms, amps times ohms, volts, amps times ohms, amps times ohms, amps times ohms, amps times ohms, volts. 0 volts around the whole loop. So we can say, well, I've got 10K, brackets ID, which is that term. And then I got minus I1 plus 2K times ID, which is that term. Minus 2K, minus I2, which is that term, plus ID, which is that term, minus I2, which is that term, all equals 0. Okay. So I got ID plus ID, and I got I2 minus I2. So I can write 10K is ID minus I1 plus 4K times ID minus I2. So what I've done here is I've got 2 ID and 2 I2, and I've taken out the 2 and multiplied by the 2K to give me 4K. Well, we can start putting in the values. But first we can rearrange this to give us in terms of ID instead of in terms of, or in terms of the currents instead of in terms of the resistances. So we can change the way it's factored. So we can have 10K times ID minus 10 times I1 plus 4K times ID minus 4K times I2. All equals 0, and then we can factor in terms of ID and I1 and I2, and we can say ID, so that's a D, ID times 14K minus 10k times I1 minus 4 times I2 is equal to 0. Have I missed a 0.7? I have. Look, I left it out. Didn't even underline it. What an error. So there should be a plus there, and that should be 0.7 equals 0. And here, that should be plus, and that should be 0.7, and that should be 0. And same goes for here. We've got 0.7 missing. Yeah, lucky I spotted that one. Right, so we then have, we can start putting in the values for the currents, because we've got values for most of them. We can do 0 times 14k minus 10 times I. This is I1, but I1 equals I, so minus 4 times minus 20 milliamps plus 0.7 equals 0. That falls to 0, and we've got minus 10i minus 80, plus 80, minus and minus, plus 0.7 equals 0. So we'll take those two across, and we'll have minus I is equal to minus 80 minus 0.7 upon 10. So I is equal to 80, or rather, if you want to be really pedantic, minus 80 minus 0.7 upon 10. And that's in milliamps, because we were dealing with kiloohms and volts. The other thing we need to know is whether this new situation, 0.7 volts here and no current, affects the conduction state of the diode that we've been assuming is off. So we can work out what VA1 and VC1 are as before. So we've got a diode that was formerly positioned like that, and we have VA1 there and VC1 there. This is the anode and that's the cathode. So VA1, well, we've got no current in ID is 0. Got that from up there, and we've decided it because of the situation of the diode. So the only real current flowing in this 2k resistor, which gives us VA1, is I2. VA1 is equal to 20 milliamps. It's not minus 20 milliamps in this situation, because we've got this is the voltage arrow due to I2, but I2 is negative anyway, so we'll end up with minus minus. So that's why there's no minus there, because we've got two of them. So they're taken away. If you wanted to, you could write it out as minus minus, but I'm not going to. Times 2k, which is 40 volts, and you've got VC1. VC1 is I1, the missing current, which is 8.07 milliamps, times the 1k plus the 10k, because it's the voltage there to there. So we've got 8.07 milliamps times 10k plus 1k, which is 88.77 volts. So V A to C is then 40 minus 88.77, which is volts. And we can stop here because we've got a self-consistent situation. We've got the unknown current, and we know now that adjusting the conduction of D2 to make it on the point of conduction has not affected the conduction state of D1. D1's still switched off. So that's the end of 4B. Moving on to question 4C, we have the value of I in figure 4C at which D2 changes from a conducting to a non-conducting state. Has the state of D1 changed under these new conditions? So this is the same question essentially, but with a different circuit. So we've got a 1 milliamp current source, and we've got D2, and we've got a resistor in series in parallel, and we've got a resistor off here, and a diode, and a voltage source, and in parallel with these two we've got a resistor. Doesn't need much room to write equations. And the values are 4K, 4K, 2K. This is the unknown voltage V, and that is everything. Working with our usual mechanism, there is 0.7 volts across the diode. We're saying, what do you have to do to make D2 on the point of conduction? So the first thing we can say is, well, if there's 0.7 volts across D2, there must be 0.7 volts across the 2K resistor, in which case V is I times R, or rather I is V upon R, and we can say that this current here must be and then we can sum up the currents at the cathode of D2. So this is nodal analysis. So we're adding up all the currents that flow into this node here, or out of the node as well. Summing up all the currents. So call this one I1, shall we? They don't actually get labelled. We'll call it I1 anyway. We'll call this one I2. We'll call this one I2K. Call this one ID. And we'll call this one 1 milliamp, because that's what it is. Can you see that this is V volts above the reference? We don't know what V is, but it's V volts above the reference, where the reference is all this stuff here. And this point must be the reference minus 0.7 volts, because we were at 0 here, which is our reference, and we've dropped down this 0.7, so this must be at minus 0.7. So we've got, to get I1, we've got V minus 0.7 divided by 4K. In red, because I'm doing currents, and that's that voltage there is V minus 0.7. And then we've got I2 as well, which, now could we agree that the voltage with respect to the reference here is V minus 0.7 as well? This diode's in conduction. So we've got, for I2, we have V minus 0.7. Now that's the voltage here, so we're going after the voltage across this resistor minus 0.7, because that's the voltage on this end of the resistor, because it's 7 below the reference here. So this point is at minus 0.7 volts. So that's where the minus is the subtraction of this voltage and that voltage up there. This voltage is minus 0.7, and this voltage is the voltage on this node, which is this V volts minus the 0.7 volts of this diode. Then we've got the Ig for the 2K resistor, I2K, and we had that as 0.35 milliamps. And we know that ID is 0 because that's diodes on the point of conduction, and we know that the 1 milliamp current is a milliamp, obviously, and it's leaving the node. So if we say I 1 milliamp, fairly obviously 1 milliamp, but it's actually minus 1 milliamp because of the direction of the arrow. And you can choose the direction of the arrows, and the algebra will sort it all out for you. So that's what we've got in terms of currents in and out of the node, and we can write those all up. And all of the currents that enter and exit this node have to add up to 0. That's Kirchhoff's current law. So we've got I1 plus I2 plus I2K plus ID plus I1 milliamp equals 0. Now I'm not going to write out that because it's pretty trivial really. I'm going to substitute this lot directly, and that will yield the first expression that's on the answer sheet. So we have, I'll try and write them out in the right order as well if I can. I'll leave ID in because it's 0, plus 0.35 milliamps, plus V minus brackets minus 0.7 divided by 4K, plus V minus 0.7 in brackets minus 0.7, or minus 0.7, sorry, also in brackets. Oh, I didn't do the value of the resistor, did I? Look at that. Sorry, this is divided by, and it's I2, so it's 4K. Oops. And there's 4K there. And is that the last thing? We've got 1, 2, 3, 4 terms. 1, 2, 3, 4, 5 terms. So we've got the 1 milliamp to do as well. And this is minus 1 milliamp, all equals 0. And that's what we've got on the sheet, more or less. So we can rearrange this to get V, in fact, which is what we're after. So we need to go, right, this is 0 because that's what the question is saying. It's saying that this diode is on the point of conduction, which means 0.7 volts across it and 0 amps through it. And we need to know what we have to do to V to make that true. And this expression will tell us that. We can bring these two terms together because they're both over 4K. So this has got the same denominator as that. So we can say 0 here, so 0.35 milliamps plus V minus 0.7 plus V minus 0.7 minus 0.7 all over 4K minus a milliamp, 0. The thing that could really catch you out here is all the minus signs and so forth. So we've got 0.35 plus V plus 0.7 plus V minus 0.7 plus 0.7 all over 4K minus a milliamp, 0. This bracket we're allowed to remove, and then we can say, well, that one and that one cancel with each other. So I've got 0.35 plus 2 times V over 4K, and I've got one 0.7 left, which is 0.7 over 4K. And there is no funny partial fractions going on here, it's just as I brought them together in the beginning, I'm allowed to split them afterwards. Minus a milliamp is 0. I've just got to get this for V now, so I'm going to do 2V over 4K is equal to a milliamp minus 0.35 milliamps minus 0.7 over 4K, and then I'll do V is equal to 2K, so I've divided 3 by 2 times that lot. And I should just be able to get an answer for V now. This is a voltage, so just to break with tradition, I'm going to write it in green. What we've been working on here is currents. That's a current. These are all currents because they're voltage divided by resistance, and that's a current as well. So that's why I've been working in red. So we now need to go back to the circuit, in fact, which I've removed. We need to know if the current in this diode here is still more than 0, because if it isn't more than 0, it means the diode has switched off due to this diode being on the edge of conduction in the new state. So we'll have to do some calculations to figure that out. So we've got 0.95 volts here, and we know that this is minus 0.7 volts up here because it's the reference minus 0.7. And we can say, well, the current in the 4K and the 2K, well, the current in the 4K has got to be whatever current's in the diode, and the current in the 2K is the sum of the whole lot. So if we say, assuming it is conducting, what do we end up with in terms of current? Well, we've got 0.95 here, minus 0.7 will lead us to 0.25. Why did I not do that in my head? And this is minus 0.7, so the current, or the voltage across 4K is now 0.7 plus 0.25, 0.95. Now if you've got a different answer, then you'd have to be really worried. So we can work out what the current is by Ohm's law. So I is equal to V upon R, which is 0.95 divided by 4K, and that would be 237 micrograms. 237.5 in fact micrograms. Now if we come to the conclusion that in fact this voltage was lower than this one, if that had been say minus 0.8 for example, we'd have to be really worried, because that would mean that the current in this resistor was going this way. And if that happened, if we found that out, it would mean that this current must be going that way as well, because it's a branch, and that would mean the diode had switched off, because now the current's going the wrong way through the diode, and that won't happen, the diode will switch off. So that would mean our 0.7 was invalid, and that would mean we'd have to recalculate the circuit, knowing now that while that's on the point of conduction, this diode would be switched off. As it is, we found out that in fact this isn't minus anything, it's plus 0.25, which is bigger than minus 0.7, so there is a current flowing that way, not that way, through that resistor, and the assumption about this diode being conducting is valid.